All right, Keeper 5.3, Conditional Probability and Independence. All right, so the first part of this Keeper discusses what we call a conditional probability. The conditional probability is the probability that you're looking for based off of something that you already know happened, something that you know for sure happened. So like in your scenario, it's going to say something like, knowing that this happened or given that this happened, find the probability of something else. That's, again, is your conditional probability. I'm not looking at it as far as the grand total. I don't want to know, what the probability is out of the grand total. I want to know it out of whatever condition I placed on the scenario or the situation. Here's our little notation for the conditional or the given that. This straight up and down line means given that. So in other words, this says the probability of B given that A has already happened. All right, so here's an example. It says, consider the two-way table on page 314 of your book. Define the events E. The grade comes from an EPS course, and L, the grade is lower than a B. So the first question says, find the probability of L. Well, again, L is that the grade is lower than a B, so here's below B. What I want to do is I want to total these up. And so below B is 3656 out of the grand total. So out of the 10,000. So 3656 out of 10,000, that gives us 0.3656. There was no condition there. There was no special clause there. So we just found the probability straight up, just like we did in Keeper 5.2. The next question, though, says find the probability of E given that L has already happened, or given that we know L. In other words, find the probability that the grade comes from an EPS course given that the grade is lower than a B. So this time, I don't care about an A or a B. All I care about is the grades that are lower than a B, because they're telling me, they're saying, this person's grade is lower than a B. What's the probability of them being in an EPS course? So in this case, I'm only going to look at this lower than a B or below B category, and I'm going to find the cell that's for the EPS course, which is 800, and this time I'm divided out by the 3656. In other words, I'm not dividing it out by the grand total. I'm dividing it out by what I know is to be true, what I know was given. All right, so we divide it out by the 3656, and we get 0.2188. Now this next question, I just flipped it around. What's the probability of L given that E happened? In other words, what's the probability that the grade is lower than a B given that it comes from EPS course? This time my given that is the EPS, so that's the 1600. And lower than a B would be 800, so I'd simply have 800 out of the 1600. Again, not out of the grand total, out of what I know is given, to get the 0.5. All right, the next concept I want to talk about real quick is independence. And so if two events are independent, they have no effect on each other. Now that's different than mutually exclusive. Remember, mutually exclusive is that if you have two events, they can never occur together. They can't occur at the same time. Versus independent, they can occur at the same time, but they have no effect on each other. So one thing isn't making another thing happen. It's not causing another thing to happen. They're totally independent of each other. The way you check for independence is you do the probability of A given B, and you want to make sure that it actually equals the probability of A. In other words, what this is saying is, if you have the probability of A given B, and B has no effect on it because they're independent, then it won't change this probability, and you should still get out the probability of A. Vice versa, same thing here. If I have the probability of B given A, but A has no effect on B because they're independent, then this should just equal the probability of B. When you're checking for independence, you literally need to check both of those. Now, if the first one works, you still have to check the second one. But if the first one doesn't work, then you can stop right there. They're not independent. So here's the example. It says, are the events male and left-handed independent? Well, let's first check the probability of left-handed given male. So if I know they're male, again, I don't need to look at females at all. I'm only going to take the male category. And I want the left-handed people, so that's 3 out of the total 23 males. So 3 out of 23 is 0.13. Now, to check to see if it's independent, I have to make sure that actually equals the probability of left-handed. Well, if I look at the probability of left-handed, there's a total of 7 out of your 50, and I get 0.14. In other words, these two things don't equal. What that's telling me is that the probability of left-handed given male is different than the probability of left-handed, meaning that male has some effect on whether or not you're going to be left-handed or not. All right, so to sum it up, it says these probabilities are not equal, therefore the events male and left-handed are not independent. They are influencing each other in some way, some shape, some form. All right, now last keeper, 5.2, we talked about our sample space and how we can just like draw our sample space or just state what the sample space is. Oftentimes it's very easy to create a sample space with a tree diagram. Matter of fact, this is one of my favorite ways to create a sample space, especially when you're dealing with a lot of different or moving parts. All right, so here's a little example just so you can see what I'm talking about. You should have seen this probably in middle school sometime, but just an example of what I'm talking about. Consider flipping a coin twice. What's the probability of getting heads? Well, I could draw out a sample space using a tree diagram. So I toss a coin once, I have 50% chance of getting heads, 50% chance of getting tails. Well, then I flip it again, I can get heads or tails. And again, it's 50-50. Again here, flip it again, I get 50-50. All right, so this is my sample space. This is showing every single possible outcome, as well as it's showing the probability model as well, because it's giving you the actual probability for each toss or each flip. So if I want the probability of getting 2 heads, well, here I have heads, heads. Everywhere else there's a tail somewhere in it. So the probability of getting 2 heads would be 1/2 times 1/2, which is 1/4. All right, so we already talked about 5.2, we talked about the general addition rule. This keeper, we're talking about the general multiplication rule. Your multiplication rule you use when you have an and situation. So this and that, or basically an intersection situation, you use your general multiplication rule versus your general addition rule is for or. All right, so your multiplication rule is probability of A and B equals the probability of A times the probability of B given A. In other words, I just multiply the probability of A times the probability of B given A. All right, sorry, I went too fast. All right, so again, here it is again, nothing different. The only key thing that you need to know here is that if your A and B are independent, you don't have that given them portion. So instead of like, if I flip back, instead of looking at it like this where you have the probability of B given A, well, since A has no effect on B, you just have probability of B here. So if they're independent, has no effect on one another, your probability of A and B is just probability of A times probability of B. Again, that's only if they're independent and if they have no effect on each other. All right, so we could take our general multiplication rule and we can use it and manipulate it to get an actual formula for your conditional probability, what we were talking about on the first slide. Now, your conditional is really, really easy to calculate if you're given a two-way table, but if you're just given a whole bunch of information, it's a lot easier just to use the formula. So what I'm going to do to get a formula for the conditional is I'm going to take this general multiplication rule and I'm going to divide both sides by the probability of A. In other words, I'm trying to get the probability of B given A by itself. So if I do that, I get the probability of B given A equals the probability of A and B over the probability of A. And that is our conditional formula. You guys need to know that formula. That formula is very important. It will come in handy a lot when you're solving problems. Anytime you have a conditional problem where you're not given a two-way table, you'll use that formula. All right, so just a short, real quick example. If you remember back from Keeper 5.2, we did an example about who reads USA Today and who reads the New York Times. We had a Venn diagram that we drew. We also did a two-way table for it. So let's say I'm trying to figure out what's the probability that a randomly selected resident who reads USA Today also reads the New York Times. In other words, if I know the person reads USA Today, what's the probability that they also read the New York Times? So here we have our formula probability of B given A equals all of this. In this case, my B is New York Times, all right, because I want the probability that they read New York Times given that I know they read or they read USA Today. So A is USA Today. All right, so using this formula, I need to figure out the probability of A and B. Well, that's just the intersection of A and B, which is 0.5, over the probability of A. Well, the probability of USA Today is not 0.35, but it's 0.4. Remember, it's the whole circle, so 0.4. What I'm going to do is I'm going to take that 0.05 times the 0.4, divide those two out to get my conditional probability of B given A is 0.125. All right, talk a little bit more about this in class. See y'all tomorrow.